The last video I posted was on making carbon quantum dots, and I got a lot of really great questions on that video. This question is from YouTube, and it's from Vsor, and it says, "How thin could you get the spectrum under ideal circumstances of for filtering? Like, is there a quantum principle that prevents it from being too fine of a spectra?" Also, if you don't already follow me on YouTube, definitely go follow me over there. But to answer this question, I thought I would give a background on quantum dots and interpreting UV vis spectra. So, if you look at the spectrum of a quantum dot, you see that there's a lot going on. But each of these features in the spectra, the absorbance and emission spectra, have different physical meanings, and I'm going to go through them one by one. We start out with the absorption spectra. We see that quantum dots have this initial absorption peak, but then they have this really long absorption tail. And this is due to the electronic structure in the material. This is how charge carriers can move around. These are all the different electronic states that exist in this material. This absorption peak right here is the band edge. This is where the energy gap essentially between the valence and conduction band is, and this is the energy at this. So this is a near infrared emitting quantum dot. So it has a band edge in the near IR at 1400 nanometers. It helps to look at something called a energy diagram to understand why these different spectral features show up in a UV-Vis and IR spectrum. And so if you see here in a energy diagram, you have initially your bulk material. So this is your bulk semiconductor. The different energy levels are basically continuous. What happens when you shrink a material down to such a small size is that you start to restrict how the charge carriers in that material, the electrons and electron holes, can move around in that material. And so you start getting quantization. They can only exist at certain energy levels, others are forbidden essentially. And so you start to see kind of gaps in this continuous band structure. So this right here, the absorption peak is this gap between the valence band and the conduction band. And this tail you see are kind of these higher bands in the conduction band and the valence band. So these features here. This restriction in the allowed energy levels or quantization is also why quantum dots are sometimes referred to as artificial atoms because they have these really discrete quantized energy levels, the same way that atoms do. And so the end result, at least in some materials, is that you'll get these really well defined peaks in the absorbance spectra. You can see here, this is the 1s transition. So if you remember from like chemistry, you have like your 1s, 2s, 2p, it goes on. But those are those electronic transitions in the quantum dot, and you can see them in the absorbance spectra. Next, there's something called the emission or photoluminescence spectra. That is where they are the energies that these quantum dots are emitting light at. And so you see it has some width. It's defined in science as the full width half max. It's the width at half of the maximum intensity of the peak. And this also has information in it. This is telling you things like the size dispersal of the quantum dots. So typically when you measure quantum dots, they're in solution. So you have thousands or millions or billions of these little nanoparticles in solution. So you're getting an average of all the different emission spectra or absorbance spectra of these different materials. So that shows up in the full width half max of the spectrum. So if the particles are more uniform, the full width half max of the emission and absorbance spectra will be narrower. And if they're less uniform, it'll be more broad. And you've probably also noticed that the absorption and emission spectra don't line up. There's a little shift. That shift is called a Stokes shift. A Stokes shift is telling you about how the electrons are moving around within the material. So not only are there electronic transitions, between different energy levels, there's also vibrational states. How the atoms, the physical, atoms are moving around or vibrating in that material. So the electrons can move between different vibrational states, and so that slight shift you see can be due to energy losses, essentially between uh, the electronic states and the vibrational states. So whenever a quantum dot absorbs a high energy photon, what happens is an electron in that material gets promoted to a higher energy state, but to relax back down to that lower energy state, it has to give off that energy back. so it releases light, but it's never at the same wavelength that it was absorbed at. It's usually at a lower wavelength, and that shift in the difference between the absorption and the emission is that Stokes shift, and this is because of these different vibrational transitions that are happening. So between the electronic states, there's vibrational states, and so the electrons kind of move between these vibrational states before going back down to the different electronic states. So that's where that Stokes shift comes from. Another question that they asked was, is there a finite limit, or what controls how broad or narrow that these peak or spectral features can be? And yes, there is something that controls how broad or narrow that they can be. There are various types of broadening that can happen in these spectra, and they're called inhomogeneous and homogeneous broadening. Homogeneous broadening is due to the particles or the emitters experiencing some different environment. So, for example, if I place them in one solvent versus another, or different temperature environments, or pressure or magnetic fields, for example. Inhomogeneous broadening comes from the emitters in the particle experiencing different environmental conditions. For example, the atoms at the surface experiencing a different environment than the atoms at the core of the nanoparticle. This can arise from things like surface defects or traps that will cause the fluorescence to shift, or you result in losses of fluorescence, or it can be done intentionally through a process called doping, where you add small amounts of another material that can shift the electromagnetic properties of the material. But yeah, this was a really great question, and I hope you continue to ask more like this. Until next time, though, this is the Mad Bioengineer signing off.